Welcome guys. Today's topic is electronic properties and optical processes in semiconductor. So subject is IODEC, integrated optoelectronics devices and circuit. So what are the electronic properties we are going to study? These are listed here. First is carrier effective mass, then effect of temperature and pressure on energy gap, third carrier scattering, fourth conduction properties, fifth recombination phenomena. So first we will understand what is the effective mass. Effective mass m of any carrier electron or hole is given as it's a as square h cut square divided by second derivative d2 e by dk2. So k is the momentum operator, e is the energy of carrier, h is the Planck's constant, h cut is nothing but h by 2 pi. H by 2 pi is written as h cut. So where from this effective mass comes? So we write a star notation on the m, which is called effective mass of carrier. It may be electron or hole. So where from this comes? Let me start with the energy. The proof of this is energy of electron is nothing but half mv square, and we can write this 1 by 2m, and we can multiply 1 by m at the top. It is mv square. Mv is nothing but the momentum p, so we can write p square by 2m, and p is nothing but h cut omega by 2m. So we are getting h cut is h cut, not don't write omega here. So p square by 2m. So p is given by h cut k. We'll find this later. Momentum is given by equal to h cut multiplied by k. K is the momentum. So p here we can replace cut square by into k square. So the expression comes h cut square by 2m into k square. So this is the energy. Now if we take 2 times derivative of E with respect to k. So E is the quadratic function of k, which comes like a parabola. E and k relationship is nothing but the is proportional to k square. So this type of EK diagram we get in general. Now if we take derivative of E with respect to k, we'll find dE by dk. Let me clean. So you can write dE by dk, so it will be 2k times this, so it will be equal to 2k times h cut square by 2m, and 2 cancels. If we take once more derivative, d2 e by dk2 will be equal to, say, this constant comes h cut square by m. So m is nothing but h cut square divided by d2 e by dk2. So this is the proof of effective mass. To understand the proof of why the momentum of any particle is equal to mv is written as h cut k, we need to understand the quantum concepts. So in quantum concept, psi is the wave equation of any particle. Particle may be electron, proton, hole, photon, phonon, and psi into psi conjugate is written as equal to psi square, which gives the probability of a particle. And there are classical values which are getting converted to quantum operator. So equivalent part are E is the momentum in the classical, and in quantum operator its equivalent is h cut by j into del by del x, and E is the energy in classical. In quantum operator equivalent is minus h cut by j del by del t. So these are very much important operators which we deal to find out all these formulas. So for psi k, if k is the momentum, then wave energy of electron or particle is given as ukx, which is the some potential energy, multiplied by jkx. X is the position, k is the momentum. So this is the wave function of electron. Now to find the expected value or average value of any quantity, say fx, we must multiply this fx by probability function and then integrate minus infinity to infinity throughout the space, and we must normalize this integration with the total probability minus infinity to infinity px dx. So the wave function is given as u multiplied by e j k x. Why it comes this nature? Because the crystal is the periodic function with k, that you need to understand lattice space where from k comes. So if this is the crystal situated at a distance of L crystal points, then 2 pi by L is the k vector, and the electron wave is given by the wave constant k is equal to 2 pi by lambda. So L, k is the propagation constant or wave vector of electron, where k is defined by 2 pi by L in one space, where L is the distance between the two crystal points. And expected value of any function fx is given by this expression, where the probability function must be multiplied with the fx and integrated, and here must be normalized probability function divided by the probability function integration with x throughout. So for the, if you want to find expected value of p momentum operator, then psi square, first we need to find the probability is nothing but the psi square, psi into psi conjugate. So psi conjugate is nothing but u square multiplied by this into this. So this is earlier there, conjugate is minus jkx. Now if you take the expression, this expression, so it is nothing but this value is written here, and we must multiply this value with p operator. So what is p operator? H cut by j del by del x. So this is here h cut by j del by del x divided by this. So what will be the final value? So p is nothing but equal to, when we take derivative of this part, it comes jk ex, jk into e power jx. So if we write this numerator, we'll get u square integration u square e minus jk x into h cut by j, and derivative is j into k into e power jk x. So this term cancels out, and here j cancels out. It remains h cut k, which will come out here, h cut k. So you can remove this outside, and denominator again u square dx. So u square dx cancels out, and we find p is equal to h cut k. So this is the proof of p is equal to h cut k. So we can recap the concept once again. P is the momentum of the electron or carrier is h cut k, and energy is equal to half mv square, which is equal to 1 by 2m p square. Now p we can replace with h cut k, we get h cut square by 2m into k square. So E is quadratically varying with respect to k. So ek diagram we can find like this, ek diagram, and if we take the second derivative of E with respect to k, from this equation we get h cut square by m, where from m comes this. So this is called effective mass. Again, why then we are taking the m star? Why not m? So effective mass is the concept of, because mass is not same in all the three direction x, y, z. So we can take the, it's a zero level of energy is not this, it's energy EC level, and EV is here. So this is gap. So it's normally written as E is equal to h cut square k square by 2 m star plus EC. So why this m star comes? Because if we take all the three direction x, y, z, kx, ky, kz, so in these three directions masses are not same. So suppose this is longitudinal direction, here mass is ml, and these two are the transverse directions. So here mass is mt, here mass is mt. So these two direction mass are same, but this direction mass is different. So we take here m star is the nothing but the derivative of this E with respect to k, and k is nothing but k is equal to kx I cap plus ky j cap plus kz k cap, kz k cap. So k is the summation of all these vectors x, y, z, where kx we can find from here. See, kx is equal to p by h cat. So since masses are not same, so k are also different in this 3 dimension, and hence the effective mass is the modeling of one vector such that we can divide this by m. It's just like a modeling of all the 3 masses into one mass, so it comes as a effective mass. So effective mass gives us this quadratic pattern. If we don't take this, if we take different separate mass of longitudinal direction, transverse direction, this will not look quadratic. So actual EK diagram may be like this, actual EK diagram, but to deal it perfectly with good equations, we model it with effective mass m star, and when we replace all the masses with m star effective mass, then we can take the quadratic dependency of E with respect to K. So this is the beauty of effective mass. Hope you might have understand this. So second point is the effect of temperature and pressure on EG band gap. So effect of temperature can be modeled as this: EG, energy gap or band gap at any temperature T, is given by energy gap at 0 temperature, absolute 0, plus AT squared divided by T plus B, where T is the temperature. A and B are the constant. Here are the some data for gallium arsenide and indium phosphide. So Eg0 is the energy gap at 0 temperature, absolute 0 Kelvin. So these are the value 1.5 electron volt. So and for indium phosphide it is 1.42, and AB are the constant. This, so its unit are electron volt per Kelvin, and this is Kelvin. So this is the dependent of temperature. Energy gap dependent on temperature. Compressive hydrostatic pressure decreases the interatomic spacing, which results in an increase in the fundamental energy band gap. So it's when pressure is increased, it may change stress or strain, which reduces the interatomic spacing, which means reduces the lattice constant, and lattice constant is directly connected with the k vector, momentum vector k, and hence energy band gap changes by the applying of pressure. There are some modeling equation, but I am not going to the depth here. Now, next point is scattering phenomena. So what is scattering? When we apply potential in a semiconductor, potential difference across its end, the carrier get drifted or diffused from one side to another side. So its movement or its mobility is limited by some factors like impurities, defects, or phonons. So the limiting of its movement or mobility of carrier is nothing but the scattering phenomena. So it arises due to these 3 things. So the scattering of different types: impurity scattering, phonon scattering. So when the scattering is limited by impurities or defects in the crystal, it's called the impurity or defect scattering. And when it is carried out with the help of phonon, it is called phonon scattering. So what is the phonon? It's nothing but the quantum or the smallest value of lattice vibration. So when a lattice is heated up, lattice temperature increases, so atom vibrates to its mean position, and that vibration is measured in the smallest form, which is called the phonon. So phonon also observes the energy of electron, and when electron moves with some energy, it transfers its energy to lattice vibration in the form of phonon, and that is called the phonon scattering. And when there are some impurities ions, plus or minus, so when it is n type, it is plus ion will be there. When p type, it is negative ion will be there. So in these 2 cases also, when carrier are transmitting, conducting from one side to another side, they get heated by these things, and some energy are lost to these impurities, and this type of impurity is called the impurity scattering. And there are some dependency of mobility, how mobility is changing. So that is given by the expression and some graph also. So I am going to show you that graph. So the effective mobility mu is inverse of effective mobility is equal to 1 by mu L plus 1 by mu P, where mu L is the mobility limited by the impurity and 1 by mu P. Mu P is the mobility limited by the phonon. So at very high temperature, carrier starts increasing and mobility starts decreasing, and this is the dependency of mobility on temperature. At lower temperature, when temperature increases, there is the phonon effect. So mu P dominates up to this value, and mobility depends on the temperature with this expression. And at very high temperature, carrier concentration increases very highly, and this is the plot of mobility with respect to temperature. So this is the dependency of scattering onto the mobility. So here is the conduction properties. Conduction in semiconductor is carried out by these two phenomena, drift and diffusion phenomena. And in drift, when electric field is applied, we get the drift phenomena, and it's nothing but sigma conductivity is given by Q whole into n mu n plus p mu p, where n and p are the carrier concentration of electron and hole, and mu n and mu p are the mobilities of electron and hole respectively. And in diffusion phenomena, current density J is given by Q dE dn by dp minus dn by dx minus dp by dx, where n and p are the carrier concentration of electron and hole, dE and dp are the diffusion constant, and so the total current density we can add this value and this value, and total whole current density can be added by this and this value. So what is next topic is recombination processes. Whenever there is excess of magnetic carrier in a semiconductor, there will be electron hole recombination. So because magnetic carrier do not change too much, the change which can be seen in the magnetic carrier, so the magnetic carrier can be increased because of photoexcitation or injection effect. So if there is p-n junction, we forward bias it inject magnetic carrier from p to n side, and if we shine light on this, again there will be some injection of magnetic carrier within this section region. So because of this magnetic carrier, there will be electron hole recombination. So the recombination rate depends on the magnetic carrier concentration. So this is the excess of magnetic carrier. So P was suppose P naught is the initial concentration of hole in n-type semiconductor, and after doing these two operations, photoexcitation or injection, the final hole concentration becomes P. Then P minus P naught is the excess of magnetic carrier, that is excess of hole in n-type semiconductor. So how it is changing? Rate of change of this excess of hole in n-type is the recombination rate. So this is divided by some time constant tau h. So tau h is called the recombination constant of for hole. Similarly, in p-type semiconductor, n is the magnetic carrier. Suppose n naught is the magnetic carrier before this photoexcitation, and when photoexcitation was done, some amount of magnetic carrier n is generated. Suppose that is n. So this is the excess of magnetic carrier generated, and when this is divided by time constant tau e, it gives the recombination rate for electron. So this is electron recombination rate, this is the hole recombination rate, and both depends on excess of magnetic carrier concentration, and tau h is the recombination time for hole, Tau E is the recombination time for electron. So recombination takes place with the help of electron capture or emission, either or hole capture or emission. So here is the diagram to represent all these four phenomena. Suppose this is the valence band and this is the conduction energy band, and there are some impurities, some excess of electrons here near the conduction band, and there are some of the impurity ions, plus ions are here, Et. So some electrons will be captured by this ions, impurity ions. So this is called the electron capture. So some of the electrons from the conduction band will be transmitted to the ions of the impurity. This is called the electron capture. So electron emission. Some of the electrons here will be again emitted back to the conduction band. So this is the Et. Again this is the E and this is the hole related to E. So some of the electrons will again emit from the impurity level to this conduction band. It is called the electron emission. So this happens when n-type impurity is doped, because when n-type impurity is doped, Et will be near to the conduction band and the dopants will be of positive ion, donor ion. And when it is doped with the p-type, we are getting this some impurity level, which is the cation negative ions, near to the valence band, and this is due to the acceptor levels. So some holes from here will be captured to this level. Some hole in the valence band will be captured. So this is called the hole capture, and sometimes some holes will be again emitted from the impurity level to the valence band. So this is called the hole emission. So this is hole captured, hole emission, electron captured, electron emission. So all these four processes gives rise to the recombination processes, and all these four equations are modeled. After modeling, we get the final recombination rate, which I have stated earlier. R is equal to 1 by tau H P minus P naught, and R is equal to 1 by tau E n minus n naught. So all these two equations comes from when we model all these four phenomena and get the expression. So we'll discuss recombination process in detail. There are some important processes of recombination like Shockley-Reed-Hall recombination, SRH recombination, Auger recombination, surface recombination. So all this we'll discuss in detail in next videos. Thanks for watching.